So I have the honor of opening this session on this digital and security. Maybe you would be a little bit scared of the word quantum in this title, or maybe out of scope if you never heard about it. But actually, I'd like to point out that when you look at how I found the money for the research of this kind of project, we are actually within this digital European project at the same level of any other new digital technology that is being put forward for the future infrastructure of telecommunication. But it's true that myself, this is my first tech conference. I'm an academic. I'm leading a new team of researchers on experimental photonics. And I do not just quantum communication, but quantum metrology, computing, and all these kind of things. But for the purpose of this talk, we are going to look at this fully meshed quantum network. So before getting in depth of the subject, I really wanted to debunk a few myths. I don't know if you're familiar with quantum or not, but at least I want to make sure that we agree on a few things. So the busted myths, I would just select three main things that I think people are misled from a broad audience publication and movies and stuff like this. So quantum physics is not spooky. It's not something weird that we don't really understand and all. It's a sound theory, right? Don't trust this kind of representation from movies like the Ant-Man movie and all. And it's just a good theory that came in more than a century ago. Next. Apparently, next here. And this theory, why is it called quantum? At the time, something very important was found, that the fundamental constant, the Planck constant, and it was an endeavor to try to understand the thermal radiation, the power spectrum of thermal radiation, and Planck had to really think very differently to model this exchange of energy with electromagnetic field. And the fact that it made the assumption that the exchange could be made by discrete packet of energy, very small amount, but discrete. That's what he called quanta of energy, was all you needed in the theory to be able to properly model this energy being radiated by any corpuscle in the world, in the universe. So that's why where quantum theory started to appear. And it's not something weird, it's not something that we don't understand, it's something you have every day in your everyday life, in your laptop, in your phone. I mean, there was what we call a quantum revolution, and this quantum revolution, so I wanted to point out with this slide that quantum theory for me looks more like this, so it's a lot of math, and this first quantum revolution enabled the era of the transistor, lasers, and atomic clocks, enabled everything that you use now. So it has been validated, right? It's not something spooky or weird. That's my first myth that I wanted to bust. Thanks. But the second myth is, if you heard about quantum, I'm sure you heard about this Schrödinger cat experiment. So we are not sadists, and we're not torturing cats, right? It's an experiment of thought, but it's often misquoted, or people heard about a cat in a box that is dead and alive, but just by curiosity, you know what's missing? Like the cat is not alone in the box, but there is something else in the box, right? To say that it's dead and alive. And it's a small glass of poison. But once again, it's not the fact that there is poison in the box that was the point that Schrödinger was trying to make here. Is the fact that the trigger for the poison was a quantum system. And it's because at the beginning of quantum theory, something very weird arose, and they didn't really know at the time, was it something physical or something that came out of the theory by us not understanding fully what we were describing. It's the superposition of state. The fact that in nature, at the quantum scales, there could be state of matter that are in superposition. And that was the thing here. They put the idea in the experiment here was to have a radioactive element that has a probability of decay, and if the Geiger counter made a click, it would break the vial and the cat would be dead, right? And this superposition was just Schrödinger trying to make it absurd that does it mean that the cat is also dead and alive because we didn't open the box? And because they had trouble accepting this behavior at the quantum scale. So if you're interested about it, there is a whole theory about when do we go from quantum behavior to something more classical, but this is another field of research. It's called decoherence, but it's important to understand this cat myth is not a weird experiment where we torture cats, right? We are physicists, we want to understand nature, we're not torturing anyone. But there's a special resource, the superposition of state, or maybe you heard about entanglement, they actually gave us ideas. I say us, but I mean the physics community as a whole. And these ideas are the road toward what we call now the second revolution in quantum and the quantum world. And this is what the buzz you've been hearing about the last few years, the quantum computer, quantum key distribution, and quantum metrology. That's all the kind of application because we were more and more mature technologically to harness those new resources from the quantum world to bring them in the macroscopic world with actually application that it took a long time to arrive. But quantum theory is sound, and we knew that we could do this kind of things because it was proven to be accurately describing nature, right? So what I want to focus on as my, let's say, third myth, and this is important for this lecture, is because I'm going to talk to you about network of QKD, which is what we call quantum key distribution. And quantum key distribution, there is often a myth for those of you that knows about quantum, that were bored by the beginning of the presentation and knows about quantum key distribution a little bit. There is so often a misled information that people think that physicists, they came with QKD and they want to tell to modern cryptographers that we solved everything, that's the perfect way of encrypting. It's not an encryption. Yeah. It's just a key exchange protocol. This is important. And often we say in lecture that it should be called quantum key expansion because like other primitive in cryptography, it needs a pre-shared key to start. So, of course, with subsequent rounds, you can use the QKD key generated to feed back into this pre-shared key. So there is no real issue with scaling a network with it, but somehow it has to be mentioned because it's also a myth that some physicists propagate by teaching to young students the power of QKD, and sometimes they took the shortcut and say, oh, we do one-time pad and it's perfectly secure. We know, like modern cryptographers, that one-time pad is not a realistic scheme for every communication, right? So just third myth busted, and we can go into the real summary plan of this talk, which is about quantum networks. And for that, I need to give you a couple of definitions because even among physicists, we have different way of talking about networks. And I want to give you a little bit of background into the state of the art of what type of QKD protocol can be implemented and why I prefer to use an entanglement-based protocol for my research to make actually fully meshed network. So what is a quantum network? So for computation, it's actually just distributing a lot of qubits. Those states that I told you like can be in a superposition of 0 and 1 can be used to do computation. And if you send a lot of qubits to a quantum processor, you can have a cluster like in classical computers that will give you more power for computation. But for me, I prefer to call this a quantum circuit or a cluster of quantum computers, but I don't like the word network for it. I'm from the quantum communication community, and for me, QCOM is more about transmitting a few qubits over long distance to link remote partners that have dedicated application like cryptography. So that's why I mentioned QKD earlier, and that's the focus of this talk. So quantum key distribution, if you've never heard about it, it's a protocol that was thought of in 1984 by Bennett and Brassard, and it's actually a very simple thing that even if you don't have a strong notion of physics, you can quickly understand because, I mean, you all know that light can be polarized. You went to the cinema with 3D movie and all, and the powerfulness of having superposition of states means that if you make a measure of something that is polarized horizontally, for example, if you take the state 0 over here and you project it on the wrong basis, the orange basis, you will have half a chance to be diagonal plus or minus 45 degrees, so you would have a random measurement. But if you choose the same basis for Alice and Bob, something that is horizontal will go through the horizontal filter, and something that is vertical through the vertical filter. So the whole protocol is about Alice preparing a random string, but Bob getting the good measurement basis and getting exactly the same random measurement, and so they have shared randomness. And if you're doing cryptography, you know that that's primitive to a lot of protocols, so shared randomness is amazing. But why it's amazing? It's because here you can do it in a way that you know that nobody listened to your tapped into your line. So, and it's because you have something very essential that comes from quantum physics is the no cloning theorem. It means that if someone is trying to copy your signal here, it's going to induce an error that I can detect. I can show it very easily. I mean, here, because you swap between two bases, an eavesdropper is going to have to choose as well, like Bob. So you have 1.5 chance to make a mistake. And then, because if he shows the wrong basis, you have 1.5 chance to get the good bit. You just have at least 25% error introduction in the signal when you're sending back the qubit measured. So this is a very fast proof to show you that quantum system brings you a way to detect an eavesdropper. And if you don't believe me, let's look a little bit more about what this assumption I told you that you have to make, that you cannot clone a quantum state. So it started really early on in the quantum theory that we realized that this superposition of states, those quantum states here, you cannot actually measure them with a single shot. It means that because they could be in a superposition of 0 and 1, with a single measurement, you get 0 or 1 with a certain probability. So you need to make many measurements to actually reconstruct what type of state was produced by your source. Here, imagine a source of light, like I've begun to show you in the previous slide. And this no cloning theorem, that's why I'm doing a demonstration. There will be not a lot of math in this presentation, but it's such an elegant proof that doesn't need a lot of algebra to show. So it's called proof by absurdity. So we are going to do a couple of very reasonable assumptions, and it will lead to a contradiction. So imagine that you have a state to be cloned, psi on the left, and you have an empty state. And what you would want your perfect cloning machine to do is to get 2 psi exactly the same, the clone state, right? Forget about the formula for fidelity, it's for quantum mechanics guys. But then the second assumption I will make is that if I clone the basis of my basis state, 0 and 1, of course, because of linearity, if I clone 0, I get 0, 0. If I clone 1, I get 1, 1. And it's not very difficult to imagine that a perfect cloning machine was supposed to do that, right? But now, if you take a random state, it means that you know this block sphere, you see it in other lessons, not just in quantum mechanics, but you have a sphere and your quantum state can be at on the top of this sphere, and wherever you point with your vector here, it's a random state. It can be written like this. It's a superposition of alpha 0 plus ei phi beta 1, just the coefficient to place you on the sphere. But now, if you take the assumption of the previous slide, you have to replace 0 by 0, 0 and 1 by 1, 1, right? That's just linearity. But if you actually make the product of this state, you don't get exactly the same thing. So this inconsistency shows you that something doesn't work. There is a problem, and the problem is that you cannot create this quantum machine. Is the demonstration by absurdity. That's the French translation of the theorem. I think there is another way to say it in English, but I like it, by absurdity. If you want to know more about it, you get a lot of interesting papers, including our Slovak lead researcher here in Bratislava, Vladimir Buček, that was one of the first to generalize this no cloning theorem, and you have a lot of references that you can check if you're interested. But yeah, so now I showed you that very simply we can make a system that exchange randomness with light, laser, like in any telecommunication system. But I told you that the ingredient you need is a single photon source. You need this quantum state, this single photon state that cannot be replicated if you want this security enhancements, right? And it's actually not easy to do. Building a single photon source, it's been decades of research until now. People have tried with single molecules, with semiconductor device, with default NV centering diamond crystals, People have tried to build what you call quantum dot. You get some picture here. You can even do it with photon pair sources. At the bottom, it's called heralded single photon source. It's like you pump a crystal and you get a production of a pair. And because they are produced instantly, like two photons exactly at the same time, you keep one and you announce that a single photon is coming. It's also a way of doing it. It's a lot of technical difficulties. And something happened over the years during the research. We realized that you can actually do a good single photon source, but a dirty one. Like you just take a normal laser and you attenuate it a lot. And as long as you get a good probability of getting only one photon, it's called weak coherent state, it's good enough to do the science. But it became very natural for industrial to start to say, oh, this is one of the quantum technology we can actually build. And from my time in Bristol, I had colleagues that were really good at this. And if you merge a little bit of the two platforms, silicon and indium phosphide, you can use one for the transmitter. You make a very small laser that can be attenuated to these levels. And with a receiver that's just going to analyze the photons that you send, you will get the system that you desire. So to show you how it looks like, this is just a DBR laser. It's called distributed Bragg reflector that you put on an active medium, and you get these pulses of light. If you see, this gives you the normalized power of my laser, and if I gain switch it, I get pulses with random phases, which is what you need for the protocol. And let's go to how do you do the encoding. I showed you encoding with polarization in the first slide, but actually with the laser, it's quite similar. You can have a map between the polarization state that I talked to you before and this time bin, and just have let's say the 0 that is an early time bin, the 1 that is a late time bin. And for the plus and minus bases, trust me, there is a way to demonstrate how these are conjugated bases, but you just take two pulses with a right phase link between those two pulses and you get plus and minus. So in order to analyze this, you need an interferometer. It's just a delay and pulse of light that rejoin at the end of the output of the interferometer, like you see in this small animation here. They will have either constructive interference or destructive interference, which is really natural way of behaving of light if you did a few physics courses. And the table of results, you can see it here, will have this shape. And so you have a way of implementing a QKD system with time bin, very cheap that you can fabricate on these integrated photonic platforms. And that's why industrial has been going with what we call prepare and measure. So it looks a little bit like this. My colleague in Bristol did that a few years back. You get something like half a megabit per second at 20 kilometers, which is a decent, I would say, key rate for a key exchange. So we are not going to encode encrypt the whole bandwidth with it, but it's a good primitive to enable, for example, an AES encryption scheme that needs some key at the beginning. So the question that I started with is, for this section was prepare and measure versus entanglement. And I told you that for my network, I would see entanglement more as resources. And I told you before, entanglement is hard to produce. So I give you a little bit of contradictive messages, but it's just to tell you why state of the art went this way and why now we are going another way. So entanglement became more and more feasible. Some companies are starting to make entanglement for photon pair source for QKD application as well. But mostly it's important to still investigate entanglement because it allows the graal of quantum networks is to be able to swap entanglement over any distances. The fact that you cannot clone a quantum state means that inherently any protocol you will do with a prepare and measure version or any other version will be limited because of loss. You cannot repeat the information. If you cannot clone it, you cannot amplify it. So there is always limitation in terms of distance for all of these systems. And the graal of entanglement-based network is that there is a way that it's called entanglement swapping that you can actually make, as you look at the case B, for example, you make the photon pair source in the middle, and your losses are scaling like the square root of the transmission because the source is in the middle and you only have loss on the two segments. But then if you scale it like D and you have a base state measurement in the middle, you can actually transfer entanglement that was between the photon on the source to the edge photons over there. So sorry, my pointer, yeah. I swapped the entanglement that was only on the source here to the edge. And so somehow it seems to be the perfect way to go at any distance, but it's very difficult to implement. It needs that you need to have a synchronized system to make this measurement, which is a base state measurement is also a quantum measurement that needs two photons to bunch together. And to do that, you need synchronization, you need quantum memories. It's difficult to implement, and people are working toward this, but we are far away from a high technological level at the moment, so it's not there yet. But entanglement is not, we did not forget about entanglement, and even for QKD network, I found a solution where entanglement was useful or more useful than those prepare and measure system, and that's the research I'm doing at the moment in the labs in the Slovak Academy of Science, 5 kilometers away from here. And the principle is like this. So I'm building what we call an entanglement photon pair source that is based on the Sagnac configuration. It means that I'm creating entanglement on photons on 2 different degrees of freedoms. I'm doing it by pumping with this laser here a nonlinear crystal in 2 different directions, the clockwise and anti-clockwise. It means that I'm creating photons that are HH or VV, depending on the direction, and then when they recombine on this, what we call a polarizing beam splitter, the superposition here is coherent. So I get this photon state that we call a base state that is useful to do all this application I talked to you about, and QKD in particular. You can do a QKD protocol with this. You can see it as, I told you before, you produce a pair of photon, one you keep, you encode, the other one you send. So you get this single photon nature with 2 photons. But more than that, why I'm using entanglements is because behind this, you have some, what we call spectral correlation, and the fact that we have always this energy conservation law that makes that any photons that will be spontaneously created on the left part of the spectrum will have is twin on the right part. It means that this color code that I created here means that any photon created in this spectral window will always be correlated with the spectral window of the same color on the other side. And this, as a demultiplexing strategy in the network, is quite useful. I'm taking my ETU channel of telecommunication, and I'm saying, I want these 2 users to be correlated. I want them to get keys that share randomness, and I can do this without never connecting them together. I just connect them to the same source. So that's the powerfulness of this strategy, because if you want to create a network of QKD, the fully mesh is a desired topology, right? You want everyone to be able to share a key with anyone in the network. And so that's the direction that we took, and to give you an idea of what it works, if I have 4 users, I just send 1 and -1 to Alice and Bob here. And if I want to connect a third one, I just send the wavelengths 2 and -2 like this, and so on. And very naturally, you can see that you can connect everyone with from -6 to 6, and you get a fully connected mesh with 4 nodes. So this type of strategy, so it was not like an amazing progress in terms of the way we use the resources of quantum technology, because the scaling of this is n squared, or n times n-1, right? And it means that you need still a lot of resources to connect a few people. And it's not so different by if you install a lot of 2x2 systems that, well, with 1 sender and 1 receiver that also scale as n squared. But there is a small trick that you can do, is not only the multiplexing the frequency, but the spatial. It means that why not use 2 times the same color if it's smart? So depending on the size of your network, you're going to choose balance. You have to make a good balance between spatially and spectrally demultiplexing. And as an example here, you can see it with 8 users instead of 4. Before I had 12 wavelengths necessary for -6 to +6, but now I only need 16. So I'm scaling now as 2n because I'm using 2 times exactly the same thing. You see here I have a subnet that is exactly the same as here. I just use 2 times the channel 8, 2 times the channel 7, and I just need the bottom row here to link the 2 subnets. And everyone is also fully connected. So for me, it was really good advances because I was going not to fundamental research. I want something practical. I'm making a QKD network. I don't want 1,000 users because it's not feasible. We are not going to any distances. I'm in a local area network. I want a few hundred users at most, and I need a solution for that. So getting a good scaling was the intent of this research, and we did it. So it has several advantages. It's in terms of architecture, the concept is simple, it's versatile, it's scalable, but something that is really important, it doesn't need any trusted nodes. If you look at a lot of other solutions that European Commission is funding at the moment in any other country, people went to the other solution that would be like, let's trust every node in the network and 2 by 2 make links, and every time a link is an intermediate node, it passes forward the key. So it has to be trusted. So somehow it's a downgrade in terms of security compared to a network where everyone receives the key just naturally fully meshed. So this is, for me, was the most important fact of this implementation was the no trusted nodes approach. So the key exchange layer is complex. I mean, I qualify it as complex because I'm not a software engineer. I'm sure that my colleague that will do the rest of the work in the other layer will do this easily. But yeah, the idea for the project, which is sponsored by this national Euro QCI called SKQCI here, is to at least in the next couple of years populate everything that is in blue, and over the next 10 years, the whole country. And of course, what I just demonstrated to you here is that for a metropolitan scale network, I believe that the entanglement-based solution is the best to get QKD into multiple users and fully meshed. But for other problematic, like long distance, of course, those other industrial systems can perform better on long distances or can have a niche application. It depends. You have a lot of protocols and they have their pros and cons that you need to judge before choosing them for a given link. So this is the spirit of this slide, to each his own. I'm citing a few of them, but if it's not your community, you will not know what they mean. But Twinfield QKD is really getting more and more popular for long distances. They are really good future implementations that I'm eager to discover. And of course, thank you for your attention. And we are still hiring PhD and postdocs, so if you're interested, please don't hesitate. Thanks for your attention.
And we have questions from Slido. So the first one is, how much qubits are necessary for computing somewhat really useful?
For computing? Quantum computing is not my specialty. As I said, I'm more quantum communication, but it's often the wolf that I use to sell my research. Quantum computing is going to break any cipher, and so you need quantum key distribution as or post-quantum cryptography as a solution. And it's true that the amount of qubits you need for a true quantum computer to show what we call supremacy over a classical computer is tremendous. You have this kind of graph, but I think you need at least 100,000, in my opinion, to do something meaningful. And it means a real qubit, not because those machines that they are designing at the moment, you have the qubit and the ancilla qubit. So in order to correct the error in those chips that are computing stuff, you always have to support the decoherence with a few ancilla qubit around 1 qubit that would be the logical, that would be useful to the protocol. So you need 100,000 real qubits. So you mean in terms of ancilla, you can scale even more. So it's a very difficult research area. There have been tremendous progress lately, but I think the quantum computing area still has a lot of progress to go forward. But yeah, I don't have a magic number. You go in that research you get those graphs and prediction. You can find it in articles, but everyone has their own opinion about what it will be.
Question: What are the implications of mesh queue networks for cracking existing encryption, and how soon before the world's financial system break?
Yeah, it's kind of actually the same question as the second question. I don't see it in terms of mesh because, as I said, you have to see it in terms of number of useful qubits. And my fully meshed network is for really communication application and not for computing. As I said, in a communication definition, you exchange a few qubits for cryptography, right? As computing, you will need a lot of qubits for processing. So it's not the same type of application. So I don't think you can use my network to build a better quantum computer yet. This has really this solution I presented here is a network of QKD. If you want to do a network of quantum resources fully, like in the middle slide I showed you with the quantum repeaters, only with those you can really consider application for computing and more tasks than just exchanging keys.
Next question. How will future AI benefit from research on quantum networks?
It's weird because I feel like it's like the opposite. Like I think quantum network will benefit more from AI than the opposite. Like I already started with some research where we were using neuronal network to actually calculate those tables that I showed you about. Like I did something easy for the presentation, 4 users, 8 users, but when we went to 20, 50 users, I use AI to compute those kind of tables, right? So the way you drive a quantum network, well, monitor a quantum network will need AI. I don't know in the other sense how there is stuff called quantum machine learning and all, but they are not my specialty, so I will not comment on those.
Next question from Peter is, are you using only infrared spectrum? And if so, why?
So yes, for communication, I'm using only infrared, and because it's the band at which you get the lower losses in the transmission for fiber link. So that's as simple as that. I mean, losses being such an issue, you have to start with the best transmission as possible.
And next one, wouldn't disconnecting on one of the users cause that several others would lose connection?
And no, that's the beauty of this fully mesh network is that because it's a spontaneous process inside the crystal, it's happening all the time spontaneously, and it's so fast that everyone gets photons all the time, and you cannot know in advance which gets what because it's spontaneous and it's random. So I'm not deciding at this time t 1 gets here and -1 gets here. I'm all the time -1 and 1 gets here and there, and the same for every other caller. And so all the time you get to share at least a key with everyone else. Then there is how you implement the protocol when you ask for a key to be withdrawn from the store. This can be efficiently controlled by some software-defined network, but there's nothing to do with the infrastructure itself that gives keys to everyone at the same time.
Was all questions from the Slido. Is there anybody in the room who would like to talk? Just a second.
Hello. I have two questions. First of them, what's the current state of this technology? Can we set it up in production, or is there a bigger problem on the software part of this technology, or do we have working hardware?
So the technology itself, QKD, already has a few companies selling fully finished product. The part about using entanglement source proton pair sources to do it, there is only one company that is doing it, but not with the same approach as I want to do for fully mesh network, but it's already using entanglement, and I'm collaborating with them to help bring my solution to a better industrialization level. And the point of this big SKQ series is actually to do that, to push the local solution that we decided here toward industrialization in the next steps. But there is no real technological problem to get there. Just find the partners, find the company willing to do that, find the student willing to work on this type of project, and that's all that you need, because it's nothing technical.
So no blog on the technology, on the software, and
No. Actually, I'm
you're working protocols now.
Yeah, definitely.
And the second question, a few years ago, Chinese government sent a satellite which using this technology.
Yeah.
Do you know more about it? Is it working? Or?
So that's the overall plan of this European project is actually to link every of the 27 countries, or only 26, I think, participating now, and to link them over satellite connection. Because the neighboring country, like we are lucky in Slovakia, we have a lot of neighbors, and we could do with terrestrial links for the first neighbors, but for the second and third neighbors, like I could never go back to France with my signal because it's too far away. As I told you, losses is a problem. And so the satellite is nice because it's a fixed loss. You just have to go through the atmosphere once and twice, and then you link your two partners. So yes, it's working. As you say, the Chinese did it once already. Actually, they did it a demonstration with one of your next neighbor in Austria at some point. So it's a good solution. It's just very expensive and difficult to implement because satellite is always a lot of money, right?
Question: the satellite using the laser, so it must be focused on the precise point, or it uses different wavelengths and operate on radio waves?
So there is like two different approaches, and both has been demonstrated as viable. You can be an uplink or you can be a downlink. There are advantages and inconvenients in being both. So they are both being considered by European Commission as a and at the moment there is no consensus about doing only one or of the two.
I've got two questions. The first question is, you said that all the nodes has to be connected to one source.
Mm-hmm.
Where is that source located? Who is managing that source? And do you have to trust that source at least?
So yes, that's a very good question. Thank you. So the source ideally would be located in a central location because you want every user to have as less loss as possible. So the geometric barycenter would be the optimal, right? But you cannot, in the map of Slovakia I showed earlier, like you cannot be equidistant to every node that you choose, but it's an optimal solution would be to be in the middle. And yes, you have to trust somehow the source. It's not that you trust the source and you trust the facility where you operate the source. It has to be a secure facility. When I say you don't have to have trusted nodes, every node can be untrusted, but the source itself has to be.
And the second question is, due to the limitation that quantum physics sets, that we cannot find the unknown state, right? So does it mean that in theory, QKD, right?
Mm-hmm.
QKD cannot be cracked? Or is there a theoretical framework in physics that you can actually theoretically crack?
So the demonstration of security for QKD protocol are called provably secure because there is a difference between the ideal protocol that I presented, where I say it's secured, and the implementation of such protocol. In implementation, you always have leakage, and the best example is when I told you making a single photon source is difficult, but you can maybe make a weak coherent state with an attenuated laser. And this is an implementation problem. So I made it so somehow I'm not perfectly producing one photon, so there is a leakage of information that an eavesdropper could use to extract the information, right? Because I said most of the time I have one photon, but sometimes there is two. And there is something called the photon number splitting attack that you have to be protected against. But over the years, the community has always found way to protect against every vector attack possible. And when you do your security proofs, you take into account those implementation and you say, I'm secure up to this amount of tolerance. And it will limit the size block key that you have to exchange in order to be secure. So you cannot have any size block validated depending on your losses, depending on your type of implementation or type of protocol. So all of this is taken into account. So it's not unbreakable, it's probably secure.
Thank you.